Swayam Prabha. Digital India. Educated India.
So welcome to lecture 6 of the Statistical Thermodynamics for Engineers. So we have covered a little bit of what is called fermions, what is called bosons. Now we are going to look at first the definition of macrostate and microstates in this particular problem. Okay, so let's put it this way: macrostates and microstates. Okay, so as we already saw in the previous lecture, that the particle distribution, okay, is generally specified as Nj Ej. Okay, so this is the number of particles per energy level. Okay, for each energy level. Okay, so this particle distribution, this Nj, Ej, this is a particle distribution. This is the number of particles, this Nj number of particles at the Ej energy level or the jth energy level. This particle distribution is called macrostate. This particle distribution is called a macrostate. As the name suggests, that this is a macro scale distribution of particles. Okay. Now, if we take into account, okay, the influence, okay, of degeneracy, and specify Ni, Ei. Okay. So this is the number of distinct particles in each energy state. Okay. So as you can see, if we take into account the degeneracy and we specify the number of particles in each energy state, okay, then that particular distribution, this distribution is called microstate. All right. So what will happen over here is that Nj Ej, which is basically the number of particles in each energy level, that is called, that distribution. Once I give you this, then I am providing you an account of the macrostate of the system. Now, if I provide you this, which is basically the number of particles in each energy state, number of distinct particles in each energy state, then what I am giving you is called the microstate of the system, the system's microstate. Okay, so Gj values are generally very high. So for each macrostate, again recall, each macrostate is Nj Ej, right? For each macrostate, okay, many microstates are possible. Okay, so you can understand that many microstates are possible for each macrostate. So Gj values are very high. So naturally, each macrostate, when I provide a macrostate definition, okay, there will be many microstates that will be possible. So most probable distribution because we already saw the most probable distribution is what gives you the equilibrium distribution. The most probable distribution of particles over energy levels should correspond then to the macrostate, which has got the highest number of microstate, So each macrostate has got many microstates. Okay, try to understand this. Each macrostate has got many microstates. Now, the most probable distribution, as we saw over the energy levels, that means out of all these macrostates, one macrostate will be the most probable one. And as we saw, that macrostate is probably the one that determines, okay, the equilibrium condition. Like, as we said, that, for example, internal energy has a well-defined value for an isolated system. So the most probable distribution of particles over energy levels should correspond to the macrostate, which has got the highest number of microstates. So the macrostate, that means the distribution of particles among different energy levels, that macrostate is the most probable one if it has got the highest number of microstates associated with it. Okay, so the two postulates here that we can say. One is the time average of a thermodynamic variable, whatever the thermodynamic variable may be, okay, is equivalent, okay, to its average over all microstates. Okay, so the two postulates are that the time average of a thermodynamic variable is equivalent to its average over all microstates, and number two is that all microstates, okay, are equally probable. All microstates are equally probable. Okay, so the thermodynamic average, the time average of a thermodynamic variable is equivalent to its average over all microstates, and all microstates are equally probable, not the macrostates, because the energy levels are not equally probable. As we saw, the number distributions are not equally probable. Okay, so this is like what a PDF should look like if we just plot it. So this is like a PDF. These are, say, the macrostates. So 1, 2, 3, 4, 5, 6, whatever. And you have a graph which surprisingly looks something like this, without any undulations. These undulations are not there. Maybe we should draw a little bit away. Okay, so like a freehand graph. So this one is the most probable macrostate. Okay, this is the most probable macrostate because that is the value, right? And you should note here there's a n particles are all, this is n distinguishable particles. Okay. Okay, so we already, let us just recall a little bit that if we had n indistinguishable particles, objects in m containers, okay, assuming degeneracy is 1, that means one particle per container. Okay, one particle per container. So that means if this is the level, these are the different EJs. Okay, so we already saw that the most probable, if you you recall, this is what we already found out. Okay, now if n is equal to say 6, m is equal to 2, this leads to a number like 7. Okay, so this we already did, if you recall, in the last class. Right? For degeneracy equal to 1 for all energy levels. Okay, now let us look at an example once again. Okay, as an example that will give you a more clearer idea. Say E0 is equal to 0. G0, which is the associated degeneracy, is 1. E1 is equal to, say, 1. G1 is equal to 2. E2 is equal to 2. G2 is equal to 3. Okay, and we have the total number of particles is 2, and the total energy is 2 as well. Energy will be conserved anyways. Okay, so first we determine what are the number of macrostates. And then the number of microstates for distinguishable objects, distinguishable particles, and the number of microstates for indistinguishable particles. Okay, so there is no limit, and then no limit on the number of particles per energy state. Got it? So let's look at so this is an interesting example. We can do it in a nice little way. So as you can see, so what we have to determine, this is what is given, and we need to find out the total number of macrostates, the number of microstates for distinguishable, indistinguishable objects, and we are putting no limit on the number of particles per energy state. So this is the premise. So let's take the first thing. Okay, so E2 has got degeneracy of 3, so there are 3 possibilities. Okay, so you can put, because all of them has energy of 2. All of them have energy of 2. So this is the 3 particles are there in the, and you can place the particle here, here, here. Okay, in whatever way you want. Then of course you have energy level 1, and then you have energy level 0. 0 has degeneracy of 1. This has got degeneracy of 2. So therefore there are 2 energy states. This has got 1 energy state. There are 3 energy states here, right? Okay. So the first macro state will look something like this. Right. So you place a particle in 1, E0, and then you can put the other particle in either one of these boxes. Okay, for 2. Okay, because this has got energy of 2, this has got an energy of 0. So this gives you the first macro state. Macro state 1. Okay. Now let us look at what about the other one. So again, this is like energy level 2. This is like energy level 1, and this is like energy level 0, right? So here you can now have 2 particles. Okay, you can place them all in energy level 1, because then 2 particles will carry, energy of 2, because this is 1 unit each. So this is like a macro state 2. All right. Okay. So now, as you can see, so these are the 2 macro states that are possible, which satisfies n equal to 2 and E equal to 2, this criteria, correct? So it satisfies that, okay? And this is the 2 arrangements that you can have. The system can have this arrangement, and yet it would be able to fulfill its energy requirement and the conservation of mass. So for distinguishable particles, so if you take for distinguishable particles, let's look at that. So there are two macrostates, right? Two macrostates that we found out for this very simple system. So for distinguishable particles, okay, so let's look at macrostate number 1. So macrostate number 1 can have actually 6 microstates. Correct? Because you have these 3 other possible arrangements, and for each of them you can have a distinct arrangement of E naught, right? So there are basically you can have 6 microstates. Now the macrostate number 2, on the other hand, okay, it can just have, so this is for distinguishable objects, mind you, so it can have 4 microstates. Okay, so the total number of microstates for distinguishable objects, total number of microstates is 10. Okay, and out of that, macrostate 1, which has got the highest number of microstates, which is 6, is the most probable one. This is for distinguishable objects, most probable one. Okay. It should be like, it's a very simple example which gives you an idea of what is going on. Now for, if the particles are, for example, for indistinguishable particles where there is no limit, so macrostate 1, number 1, okay, gives you 3 microstates. You can check it out yourself why it is 3. And macrostate number 2 also gives 3 number of microstates. Okay. So there is altogether 6 microstates in total. Okay. Now to determine the most probable microstate, suppose, so to determine, so you can see how the process works. To determine the most probable macrostate. Suppose we have n particles. So this is generic now, and m non-degenerate energy levels. Non-degenerate energy levels. That means G is equal to 1 basically. G is equal to 1. Okay. So in order to find that out, to find the possible particle distributions of the macrostate, to find the possible particle distributions of macrostate Wn, we already know this, we did in the last lecture. It is n plus m minus 1 factorial divided by n factorial m minus 1 factorial. Okay. So we assumed in this particular case indistinguishable particles. Okay. Indistinguishable particles. Now, if we just plug in the numbers over here, say if n is equal to 6, m equal to 2, Wm is equal to about 7. This we already did. So 7 macrostates are possible. Okay, so 6 particles are distributed in 7 macrostates in 2 energy levels. So energy levels are 2, and it is distributed in 7 macrostates. 7 possible macrostates are there. These are non-degenerate. That means degeneracy is equal to 1 at each particular level. Okay. Now, if we want to determine the number of microstates per macrostate, so let us determine the number of microstates per macrostate, if we have to determine in that So the number of microstates per macrostate, which is say WD, if we call it. So this depends on, okay, so if there are now n distinguishable objects placed in m different containers, such that ni objects occupies the ith container, this also we know, right? So say for example, so this can be cast. Now you can see how the previous lectures are coming into the picture. So this is an equivalent casting problem, that n distinguishable objects, okay, placed in m different containers. This is the question that we are asking. Containers such that ni objects occupies ith container. Okay. So therefore, this WD, or the number of microstates, now will be given as n factorial divided by the multiplicative m, I equal to 1 to n in I factorial. So the macrostates, for example, for that old problem that we had, where where n is equal to 6, n equal to 2, this particular problem. Okay, so say the macrostates. Just to give you a brief example, the macrostates in this case were 0, 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, and 6, 0. Okay. So say for macrostate 0, 6, WD is equal to 1. Okay. For macrostate 1, 5, WD is equal to 6. 6, how does it come? It's 6 factorial divided by 1 factorial, 5 factorial. Hence, the number of microstates associated with the most probable macrostate is, so therefore, the number of microstates associated with the most probable macrostate is 3, 3 is 20. Okay. So you can get an idea that what we are aiming at over here, right? So you can also cast this problem as the, we can also, also write this problem. Okay, we can also write this problem like this. We can also calculate the total number of microstates, okay, as n distinguishable objects, okay, placed in m different containers, okay, with no limitation, limit on the number of particles per container. This also we have seen earlier. So then W becomes m raised to the power of n, right? So for again the problem n equal to 6, m equal to 2, W becomes 64. This is the total number of microstates, right? We can also say that W, the total number of microstates, is greater than the most probable macrostate, and is therefore greater than the mean. So this is the total number of microstates. And this is the number of microstates corresponding to the most probable macrostate, and this is the average number of microstates. Okay, so average is basically W by W mean, something like that. Okay. So if this number n is very large, say n 10 to the power of 23, m equal to say 2, then w equal to m raised to the power of n, which is 2 into n, then w bar will be equal to 2 to the power of n divided by n plus 1. Okay, so we will look at some of these things in a little bit more details in the next class, because we have to now look at some of the other features of this macroscopic equilibrium. So right now what you saw in this particular lecture is that you can follow a procedure to calculate the total number of macrostates and the associated number of microstates with that macrostate, and the total number of microstates as well. And there can be several macrostates which are possible. Microstates are all equally probable, but the macrostates are not. So the macrostate which has got the highest number of microstates is the most probable macrostate, and that is actually related to the equilibrium condition. That is how you have a single value or a well-defined value of internal energy and stuff like that. So in the next class, we are going to see how this translates to some of the known distributions and how we can see that what is the most probable macrostate and what are the number of microstates that are associated with it. So in the next class, we are going to cover these things in a little bit more details. So here we end our lecture 6. So lecture 7 will continue this conversation of the macrostate and microstates. Thank you.